BC with a man named Thales of Miletus, whom some consider to be the father of science. He's known for his attempts to explain phenomena through theories and hypotheses rather than mythology. For example, although this may seem like nonsense to us now, one theory he had was that was water. He may have missed the mark on that one, but it's believed by some that he was able to predict a solar eclipse on May 28, 585 BC, now known as the eclipse of Thales, and a war between two local kingdoms at the time. Now fast forward to the 5th century BC when philosophers came up with a new theory that matter is not made up of just water, but a collection of elements. Water was one, the others were earth, air, and fire. Several years later, Aristotle also suggested a 5th element known as aether that made up celestial bodies, since stars probably would not be made of the same elements found on Earth. He definitely would have been shocked to learn that they are in fact made up of the elements found here on Earth. But even though we know these classical elements to be wrong, they do align quite well with these 4 states of matter we all know of. Now those are some ancient theories, but where I really want to start this video is with a story I'm sure many of you know of, which begins with a gold crown and a bathtub. In the 3rd century BC lived scientist, engineer, and mathematician Archimedes, who contributed more to the world than any other scientist of ancient times. Probably his most famous contribution was made while he was taking a bath. Archimedes needed to calculate the density of supposedly gold crown to determine whether some silver had been substituted by a dishonest goldsmith. He was not allowed to melt the crown to a normal shape in order to perform calculations though. One day while taking a bath, he noticed the level of the water rise as he got in, and he used this principle to determine the volume of the crown, since the crown would displace its own volume in water. He was able to then calculate the density of the crown using mass over volume, and concluded it was less than that of gold, proving that silver had in fact been mixed in. Later, Archimedes went on to write on floating bodies, where he continued his research into submerged objects. In this, he describes what is known as Archimedes' principle, which states how the upward buoyant force exerted on a body in a fluid is equal to the weight of the fluid displaced by the body. This principle is why you feel lighter when in water, or why it is very difficult to push an inflated beach ball underwater. Now, the story of the gold crown has actually been called into question due to the accuracy needed to measure the water displacement and how difficult that would be given the instruments available to Archimedes. Instead, a more practical technique that actually makes use of Archimedes' principle would be to suspend the crown on one end of a scale and balance it with an equal mass of gold on the other. Then when put into water, the crown would have displaced more water than the gold due to its larger volume, and thus experience a higher buoyant force, making it more apparent it was mixed with silver. Now, physics is not just a foundational science, but it's also the basis today and lead to new technologies tomorrow, and this goes way back. During ancient times, many Greeks were interested in the development of machines. For example, Archimedes is recognized for the invention of various networks of pulleys and levers. His famous quote is, "Give me a place to stand and I will move the earth." This of course has to do with mechanical advantage and the amplification of applied forces. Machines that make use of mechanical advantage allow us to, let's say, lift a car using only our own strength. One notable invention of his was the claw of Archimedes that used mechanical advantage as a weapon to defend a portion of Syracuse's city wall during the Second Punic War. Its exact design is unclear, but it worked kind of like a crane using pulleys and levers to lift enemy ships slightly out of the water, causing them to eventually flood and sink. Nowadays, simple things like bottle openers, nail clippers, hammers, bike gears, wheelbarrows, and more make use of these principles. Now let's physicist known as Ibn al-Haytham changed the way we think about light. Although a lot of research has been done since, al-Haytham is considered the father of optics. For reasons I won't go into, al-Haytham was kept under house arrest for several years, and during that time he published a 7-volume collection of books known as the Book of Optics, where he proved that light travels in a straight line. He did this through one of the first scientific experiments ever, as a lot of previous theories were simply speculation. Like at this point in time, it was still thought that heavier objects fall at a faster rate, as theorized by Aristotle. This would be proved wrong in a few hundred years though. Anyways, one experiment al-Haytham performed was he cut a small hole in a wall and hung 2 lanterns at different locations in an adjacent room. He observed that the light illuminated unique spots in the opposite room, and each formed a straight line with the hole and one of the lanterns. Also, for hundreds of years it was believed that our eyes actually emitted rays of light that would bounce off objects, allowing us to see. He was the first to say that in fact light travels from objects and enters our eyes, which is now known to be correct. Now, one thing he was wrong about, even though he did research on them, was rainbows. He assumed rainbows were an image of the sun formed from a curved mirror due to water within clouds. It wasn't until the year 1300 that Theodoric of Freiburg used spherical flask and glass globes to simulate water droplets that occur during rainfall. He observed that light refracted onto the droplets, reflected back out, or they were refracted again. Although Al-Haytham did not contribute to our understanding of rainbows directly, Theodoric of Freiburg relied on Al-Haytham's book of optics to further our understanding of them. Today, optics has applications in medicine, telescopes, astronomy, laser technology, fiber optic cables, and much more. Next up, just about 2,000 years ago, the first compass was invented. And although people did eventually use these for navigation, no one truly knew how they worked for over 1,000 years. That was until the turn of the 17th century. It was assumed for a long time that compasses were attracted to a large magnetic island on the North Pole. That was until William Gilbert came in and wrote his book where he proved the Earth was actually one giant magnet. In this book, he discusses experiments in which he models the Earth using something called the torella, or a sphere made out of a naturally magnetized material. When he passed the compass over the torella, he saw it would always point towards the magnetic pole and behave just as it would on Earth itself. The torella was improved upon 300 years later by Christian Birkeland in order to further investigate the polar aurora and why it appeared near the magnetic poles of Earth. Now, William Gilbert also did work in electricity. In fact, he is credited with inventing the word electricity, and many consider him the father of electrical engineering. One of Gilbert's inventions was the electroscope, the first instrument to measure the presence of electric charge. Over 300 years later, physicist Victor Hess would use the electroscope to discover something that would win him the Nobel Prize, but I'll get to that soon. Now, like I said, for over 1,000 years, it was believed that heavier objects would fall at a faster rate. This was introduced by Aristotle, and it seems intuitive, but of course we know now that this is wrong. The story that's been told is around 1590, the scientist Galileo dropped spheres of different masses from the Leaning Tower of Pisa to show that their time to reach the ground was independent of mass, which we now know to be true. He also showed that the relationship between distance and time could be represented by this equation. Although the basic physics here proved to be accurate, many historians believe that this story isn't, but rather it was a thought experiment. Then Galileo did work on pendulums, but also introduced the idea of relativity that would be greatly expanded upon by Einstein. Galileo stated that the laws of physics are the same in any system that is moving at a constant speed in a straight line, meaning there's no such thing as absolute motion, it's all relative. If you were in a rocket ship moving through space at a constant velocity, there'd be no way to determine if you were moving or actually stationary. Your brain probably is telling you that these asteroids are passing by a still observer right now, but look at it some more and you can probably convince yourself that the asteroids are still and you're moving past them. Galileo's work not only set the foundations for Einstein, but also provided the framework for what Isaac Newton would go on to discover. In 1687, Newton published a book called Principia that laid out the foundations of classical mechanics and is regarded as one of the most influential scientific publications of all time. In Principia, Newton stated that gravity pulls masses together. The Earth exerts a force on you, just as you actually exert a force on the Earth. He explains how this force obeys an inverse square law, so if you get twice as far from something, the gravitational force becomes 4 times weaker. And of course, the 3 laws of motion were discussed here, which is one of the first things we all learn when we take a first-level physics course. Newton was also heavily interested in orbiting bodies and celestial mechanics. It was believed for a long time that celestial bodies orbit in perfect circles, but Newton proved that actually an elliptical path would form as a result of the inverse square law that governed gravity. Newton also contributed to the field of optics. In fact, he coined the term spectrum in order to explain the colors that appear when white light enters a prism. During his studies, he invented the first known functioning reflecting telescope, or the Newtonian telescope. He did not come up with this idea, but seems to be the first to make a working one. Reflecting telescopes are very simple in design and did not use a lens, which offered certain advantages. A few decades earlier, Galileo designed what is known as a Galilean telescope that used refraction instead of reflection. It contained 2 lenses and could magnify images about 30 times in size, but flaws in the design caused images to be blurry or distorted. However, these flaws did not stop Galileo from being able to observe craters on the moon or various moons of Jupiter. Reflecting telescopes, while not perfect, did not contain some of these flaws, such as unwanted refractions, otherwise known as chromatic aberrations. Then by the 1700s, more and more research was being done with electricity. But note, at this time, no one knew that electricity came from charged particles we now call electrons. That was still over 100 years away, but that would not prevent research from being done. In fact, one of the key pieces of electrical equipment in your computer, phone, and other electronics was first formed in 1745 when Ewald von Kleist was connecting metal foil to the inside surfaces of a glass jar that was then filled with water. The goal is to charge the water by connecting it to a generator that could produce an electric charge. When Kleist then touched the foil with his hand, he experienced a very strong electric shock, one that was arguably life-threatening. But what was going on was that the jar was storing electricity. This became known as a Leyden jar. That name may not be familiar to some of you, but the Leyden jar is also considered the first ever capacitor. Capacitors exist in all sorts of electronics nowadays, and what they do is store charge. Most people who will be taking a basic physics class can expect to learn some basic circuit analysis with these. Now, the applications of capacitors have a wide range. Stored charge can be used to represent binary within a digital system. It can be used to supply large amounts of current to things like lasers and particle accelerators. They can be used as sensors. They can adjust the power in high voltage systems as needed, and so on. Moving on, when Isaac Newton was alive, he became a very powerful figure in the scientific community. Very few were willing to challenge his ideas, and this continued even after his death. But he was not right about everything, and in the late 1700s and early 1800s, Thomas Young would challenge Isaac Newton's view of optics. In 1678, the scientist Christian Huygens actually proposed that light was a wave, but Isaac Newton disregarded this and put forward his own theories. Isaac Newton viewed light as a stream of particles, since he could use his laws of motion to describe them better. In the late 1700s, Thomas Young defended Huygens' theory, and in 1804, all doubt had disappeared when he reported the results of his double-slit experiment, one of the most famous experiments in all of physics. He actually first observed how water waves would behave in a ripple tank. He saw that the waves would either combine or cancel each other out, making some kind of interference pattern. When he performed this experiment with light and shined it through two small slits, he saw the same patterns emerge, proving that light was in fact a wave. Now, shifting gears, in 1843, James Joule devised an experiment to measure the mechanical equivalent of heat. Back then, it seemed as though these were two very different things, heat being transferred versus the physical motion of something. But he eventually showed that these were interchangeable. What he did was made a device so that you could turn a handle, causing two weights to rise and fall. This would then turn a paddle that would stir the water within a container. When the weights fell, Joule noticed a rise in temperature as measured by a thermometer. After raising and lowering the weight several times, he calculated a value of about 4.14 joules, being equivalent to 1 calorie. This is the amount of energy needed to raise 1 gram of water 1 degree Kelvin. This was a little off, as we now know is about 4.18 joules per calorie. Joule also showed that energy did not disappear. It was just transferred in different forms. This then led to the development of the first law of thermodynamics just a few years later. Now, something you may not know is that years earlier in 1842, a man named Julius Robert von Mayer wrote a paper that discussed the concept of energy not being created nor destroyed, as well as the interchangeability of mechanical work and heat. Unfortunately for Mayer, he was not an actual physicist, but rather a physician, so his papers were widely ignored by experts in the field. He read up on others' experiments and used his own observations to come up with ideas, but did not have the training to present his findings in the proper way. This led to some disappointment when he found out years later that Joule got the credit for many of the topics he had been an advocate for years earlier. Joule did set up his own experiments and all that, so it's not like he stole Mayer's ideas, but we now give credit to Joule for these findings, and he even has a unit of energy named after him. And now, of course, thermodynamics has gone on to have applications in engine design, refrigerators, power plants, and more. Then, if you look up the most influential equations of all time, just about any article or video you find will include Maxwell's equations. These are the equations that tell us the relationship between electricity and magnetism. These also predicted the existence of electromagnetic waves, which propagate through a vacuum at the speed of light. Electromagnetic waves are what encompass the signals that travel through the air when we talk on a cell phone. They encompass visible light, microwaves, X-rays, gamma rays, and so on. So basically anything dealing with optics, wireless communications, lasers, etc. has its foundations rooted in Maxwell's equations. Now, Maxwell's equations did predict the existence of all these types of waves you see here, but at this time most of them really hadn't been discovered yet. We had never sent a radio signal or observed X-rays, for example. But within just a few decades, these would all be discovered. In the late 1880s, the physicist Wilhelm Röntgen was investigating vacuum tubes and external effects as current passed through them. One day while running an experiment with these, he noticed a fluorescent effect on a screen within his lab, and he deduced that a new ray was having this effect. Because these were still unknown at the time, he just called these rays X, like we do in math for unknowns. While he continued his investigation, he finally saw a radiographic image, which was a flickering image of his skeleton on a platinum-cyanide screen. As you can guess, what he had finally discovered was what we now call X-rays. Just a few weeks later, he used these X-rays to take a picture of his wife's hand, to which she exclaimed, "I have seen my own death." Only a year after this, X-rays were being used in medical imaging, and of course are still used today for medical and security purposes. For this discovery, Röntgen won the first ever Nobel Prize in Physics in 1901. He became known as the father of diagnostic radiography, and in 2004, a radioactive element on the periodic table was named after him. Röntgen's findings then inspired more research into the existence of these X-rays from other sources, and Antoine Henry Becquerel was one physicist who set out to make his own discovery. He thought certain phosphorescent materials he was working on, such as uranium salts, may have been emitting X-rays when exposed to sunlight, and he soon discovered that this was completely wrong. What was happening was that the radiation was coming from the uranium itself without the need for sunlight. By the way, at this point in time, uranium was thought of as a harmless metal, but that would soon change. Now, this phenomena observed with the uranium salts became known as Becquerel rays. That was until a few years later when Becquerel's research student, one of the most well-known physicists of all time, Marie Curie, began investigating these rays and eventually coined the term radioactivity. Although Becquerel did not get the rays named after him, the unit for how many atomic nuclei decay in a substance per second is now called a becquerel. Marie Curie and her husband Pierre Curie are probably the most well-known couple in all of science, and along with Becquerel, the three of them found that thorium was also radioactive. The Curies additionally went on to discover two new radioactive elements: polonium, named after Poland, where Marie Curie grew up, and also radium. Then in 1903, the Curies, as well as Becquerel, were awarded the Nobel Prize for their work in radioactivity. Pierre Curie died just a few years later in 1906 and is best known for the discovery of the Curie point, a temperature in which a magnet loses its magnetism. Marie Curie went on to be the first person to win two Nobel Prizes, one in physics and another in chemistry in 1911. Now, when the Curies were working on radiation research, a physicist named Ernest Rutherford began working with uranium as well and discovered two types of radiation. One that could be blocked by a thin sheet of paper, which was coined alpha radiation, that consists of 2 protons and 2 neutrons, although this was not known at the time. And another that could pass right through the paper but would be blocked by something like aluminum. This was named beta radiation and is much more dangerous to be exposed to. The most dangerous of these three I'll discuss is known as gamma radiation and was discovered in 1900 by Paul Villard. This gamma radiation was coming off radium, which the Curies had recently discovered. Gamma rays are not composed of subatomic particles, but instead are very high energy electromagnetic waves. Gamma rays can only be stopped by thicker barriers made up of things like lead and iron. These are dangerous because their extremely small wavelength and high energy makes it so they can interact with human cells, causing illness and even cancer. These are released by nuclear weapons, for example. Although this does not make this research into radiation seem positive, radioactivity grew to apply to nuclear reactors, which currently account for 14% of the world's power, and radiation is used in medicine to diagnose and treat illnesses. For example, radiation therapy is where we use radiation to specifically kill or slow the growth of cancer cells.